which is having 3 methyl group, which is connected to only 1 carbon. So just I put the 3 methyl group in a compressed way. So the same you can enlarge, you can see, you can write like this, tetrahedron structure. So here there is a steric effect in between the methyl group, so it's a bulky group. So this molecule is little bit unstable. Here also bromine is bulkier. Okay. So this molecule, in the presence of solvent, it slowly undergoes ionization, which produce trimethyl carbonium ion as an intermediate, and Br minus is a leaving group. So trimethyl carbonium ion is a planar. So the next step, attack of nucleophile on the trimethyl carbonium ion. So OH minus can attack. So assume it is a planar triangle, carbon at the center, C plus is the center. So all the 3 corners occupied by methyl group, methyl, methyl, methyl. So it is open, this carbonium ion is open. So OH minus may approach either front side, or the same OH minus approach back side of the boat. So either it attack here or it may attack on back side, which leads to both retention of configuration as well as inversion of configuration. So this product is inversion of configuration, where you can see OH minus attack on the back side of the boat, it ends with inverted structure, plus retention of configuration, where OH minus attack at the front side. So SN1 always follow with intermediate called carbonium ion, whereas SN2 transition state. That is the biggest difference between SN1 and SN2. Here the rate of the reaction depends on only the concentration of substrate. So the amount of substrate, whatever the amount of substrate, that can be decided. This one alone decides the rate of the reaction, not the nucleophile. Whether you are taking nucleophile small amount or huge amount, that doesn't matter, but the concentration of this one is very important. So rate of the reaction equal to rate constant and concentration of substrate alone. And another important point, you can see the molecule, only one molecule, the substrate molecule is involved in the first step. So this first step is a slow step, so where we can determine the rate, it is called RDS, rate determining step. So the ionization of this bond, that is a secret key point in the SN1 reaction. If the ionization is slow, then definitely the rate of the reaction is slow, still slow. If the ionization is fast, then rate is fast. So it all depends on the stability of CBr bond, CX bond. Okay. Now let us discuss about SN2. SN2. In the case of SN2, the first step is attack of nucleophile on the substrate. Consider methyl bromide. So here the opposite side, the carbon which connected to the bromine, the opposite side is free. So it is open for nucleophile to attack. So the incoming nucleophile attack on the opposite side rather than front side. So at the first step, so here it is a single step only. So at the first instance, it forms a transition state. So where you can see both leaving group and nucleophile, the attacking nucleophile connected to the same carbon, and both bear partial negative charge, both pairs partial negative charge. So here carbon assumed to have 5 bonds. So it may be as intermediate, that is the bond may be intermediate hyphen, I put it like a hyphen, but it is connected to carbon only. So it is a transition state. Penta-coordinated carbon, it is impossible. So that is why it is theoretically assumed it is a transition state. Then this transition state where OH minus push the Br out. So it donate quickly the electron to the carbon. So by the way it donates the electron, so that Br minus kicked out. So it exit from the molecule. So the entire process is a single step where we can end with inversion of configuration. So here complete inversion of configuration occurs. There is no point in retention of configuration. It is like carrying an umbrella in the windy season. So once if you carry the umbrella in a heavy windy season, the umbrella will change, the structure will change. That is Walden inversion. And another important point you can see, the rate of the reaction depends on both concentration of substrate as well as nucleophile. So the rate of the reaction depends on both concentration of substrate and nucleophile. And another important point, from the example which I cited, if you observe clearly, the molecule having hydrogen atom or less bulky groups will prefer to undergo SN2 reaction. The molecule which have bulky groups prefer to undergo SN1 reaction. That is a very important point. So this is overall discussion about SN1 and SN2. Now we are going to discuss about the factors which affect SN1 and SN2. What are all the factors which affect SN1 and SN2? So the whole substitution nucleophilic reactions is affected by 4 important factors. Number 1, substrate structure, structure of substrate structure. Then second point, the efficiency of nucleophile, the nature and efficiency of nucleophile. And the third factor which affect the SN reaction is solvent. And the fourth and yet another important factor is nature of leaving group, So SN reaction mainly depends on attacking nucleophile and exiting leaving group. So nucleophile should attack quickly, leaving group exit quickly. That is the 2 important factors which affect the SN reaction. So these 2 are auxiliary points, the substrate structure and solvent. Let us talk about efficiency of nucleophile. So efficiency of nucleophile is measured by a term called nucleophilicity. Nucleophilicity is defined as how much quick the nucleophile able to donate the electron. So the efficiency of nucleophile, how much quickly it donate the electron pair to the substrate. So nucleophilicity also differ from basicity. So these 2 points always try to confuse the students. Nucleophilicity and basicity. Basicity measures the strength of base, but nucleophilicity measures how much tendency of an atom or group to donate the electron pair. So it measures the power of nucleophile, it measures the power of base. A good nucleophile need not be a good base, but a good base always a good nucleophile. Okay. Then solvent. Polar solvents generally influence substitution nucleophilic reaction. In the case of SN1, polar solvents play a vital role because positive charge is created. So that positive charge is neutralized by polar solvents. Polar solvents having high dielectric constant. Then nature of leaving group. If a leaving group quickly leaves from the molecule, then rate is increasing rapidly. If the leaving group doesn't like, then the rate will be less. The rate of the reaction will be less. For example, compare halogens. Compare halogen atom F, Cl, Br, I. So F and I, compare F and I, fluorine and iodine. So fluorine, the extremely small size of fluorine which makes a hard base, strong base. The extremely big size of iodine which makes iodine as a soft base, that is weaker base. So this is a strong base, it is a weaker base. So weaker base, definitely the leaving group ability is more. Strong base, the leaving group ability is less. So that means fluorine prefer to attach with the carbon. It is very difficult to remove because small size, it attract the electron from carbon and which makes the carbon fluorine bond very strong. It is difficult to remove, difficult to break. Whereas carbon iodine bond, because of the size of iodine, big size, it acts as a soft base. So weaker base, hard base, soft base. This is strong base, weak base. Because of weak base, leaving group ability is more. So that's all for today's session.